Estoy grabando. Ya. Dale nomás.
Yeah. Hello and welcome, everyone. Thank you all for joining us today. It is a pleasure to have with us Sebastián Céspedes from Universidad Autónoma de Madrid. Sebastián holds a master's degree from Universidad de Chile under supervision of Professor Gonzalo Palma. Then he obtained his PhD from University of Cambridge. And after that, a postdoc position in the International Center for Theoretical Physics in Trieste. Now he's a postdoc at Universidad Autónoma de Madrid. Today, Sebastián is presenting about Lorentzian vacuum transition. So thank you, Sebastián, for accepting our invitation. And please feel free to start whenever you're ready. But before, I have to announce that we have some technical issues. So the meeting will be up to 40 minutes. So when the time is up, I will call it. And then we have to re-enter to the meeting using the same link. Okay. Go ahead.
Okay, hello to everyone. Thank you for listening to my talk. Okay, so it's always a pleasure to. So it's always a pleasure to be there, or I mean, even online and without pizzas. So it's a pity, but okay. And also because I've been, I mean, I was on the first Cosmo Pizza like, I don't know, 9 years ago or some time ago. So okay, it's always nice to go back. And hopefully I'll be there in person and we can all meet soon. So I'm gonna talk about some work I made in collaboration with Chanta de Alvis, Francesco Muya, and Fernando Quevedo while I was in Trieste. So this is mainly about vacuum transitions with gravity. And so, and this talk will be more or less like a review kind of talk about vacuum transitions in general. So it will be very broad and hopefully we can all learn from it. And please feel free to stop me whenever you have a question. Okay. So the question is, why it's important to study or understand vacuum transitions with gravity? And there are several motivations, but one that I like is that if we believe in that there is a quantum gravity description for nature, then string theory is the best candidate. And if we accept that, then when we compactify string theory to 4 dimensions, there is a large number of metastable vacua. That means that there are no one universe that is predicted within string theory, but there is a very large number from them. Each of them have different properties, like different electron charges and different constants of nature, and these are related because the fact that the vacuum properties of each solution is different. This was known from a long time, but some time ago when it was discovered that the universe was accelerating and the cosmological constant problem appeared, which is just that the energy of the vacuum from the theory is much larger than the energy of the vacuum observed. People came up with mechanisms to explain this. And one of the most important or most famous mechanism, although it's a bit infamous, is that there is something called the string landscape. So the main idea here, or the thing that I'm more interested in, is that in order to solve the cosmological constant problem using the landscape, this landscape of different vacua, I need all the landscape to be populated. And the most efficient way of doing this is through something that's sometimes called eternal inflation, which means that there are tunnelings between, I mean, if we imagine that each of these states is a vacuum, then there are some mountains between each vacua, then the most efficient way of this vacuum being populated is through quantum tunneling, similar to what we do in quantum mechanics. So in this talk, I mean, quantum decay with gravity is a problem that has been understood, or more or less well understood, for 40 years. But there are a lot of small subtleties and that make it an active field of research. So I'm gonna explain from the basics how one can compute the tunneling probability, and then what are the main deficiencies of the most used approach. So I'm gonna start with describing the theory in quantum mechanics. So this is the most standard way of thinking about this. I mean, so when we learn quantum mechanics, then we at some point we have to face. I mean, we learn to know that there is this problem when one has a potential that has two minima, and then there is a non-zero probability of going from one minima to the other minima. So in order to compute this, we need to solve the Schrodinger equation, which is, yeah, I mean, in this case, would just be a canonical Hamiltonian. So I have a momentum, and then I quantize it, sorry for the mistake. And then in order to solve this, in order to make some progress, I need to make an ansatz on the shape of the wave function. So I'll assume that the wave function is of this form. It's an exponential of is, where s is something that I will determine later. It's not necessarily the action. So then, if I replace this into the Schrodinger equation, I'll find a Hamilton-Jacobi equation. So at first, I mean, I'll be in order on the h bar parameter. So that means I'm reducing this quantum mechanics problem to a classical mechanics problem. Also, because I will be interested in energy eigenstates, then I need to also impose that the wave function has this shape. So if I do that, then I fully determine the solution for this equation, because this ds over dt will just only be E. And then I can solve for S in different regions. So then I have the over the barrier region, I mean, for a given energy E, then there will be the classically allowed states, which are here, and the forbidden states, which are there. And I can compute this parameter S over this, I mean, these three regions, and then match them. So the thing is, like, under the barrier region, then this exponent will be imaginary, and that implies that this wave function will decay. So I can compute the transition probability by defining as the transmitted wave function or the reflected wave function, and I find that this is proportional to exponential of minus BH, where after subtracting all the forbidden part, after summing all the terms, I'll get that a simple formula for the decay rate. So good. Now there is an alternative way of thinking about this. It's because if I take this action and I vary it, then it's analogous to solving the classical mechanic problem, where I have the negative potential and I want to compute solutions that bounce back and forth between the 2 points, between the two vacua. So this is just like a classical mechanic problem. So I can find the solution that goes from here to there and then goes back. And then if I replace, I mean, and this will be the action. So then if I find the solution with those boundary conditions, and if I replace it back over where CL is the bouncing solution and X naught, C tilde X naught is the background solution, this will be equivalent to computing the decay rate that I showed you before. Okay, so now we want to use this. I mean, this analogous seems a bit complicated now, but it's very easy to, I mean, the thing is, like, I'm reducing some problem which was related of solving the Schrodinger equation to finding a classical solution of some classical equation, or some equations of motion. So this can be translated into quantum field theory. So the main problem when we want to do one of these computations in quantum field theory is that in principle, we have an infinite number of degrees of freedom and make the problem untractable. So we have to make some assumptions. So first, for this case, I'm going to assume that I have Lorentz invariance. So that helps a lot. But also, I'm going to look for bounces of this Lorentz invariant solution. So, okay. So this, then I'll translate again this problem, which was the transition between, I mean, I have now the field values and the potential for the fields. So I want to find the transition probability, the probability of transitioning from the false vacua to a true vacua. And then I will compute the bounce by computing this negative potential. So analogous to making the potential negative is also the same thing at taking a Lorentz invariant theory and complexify time, and that will imply that I'm gonna go from O3,1 to an O4 symmetry. So that is very convenient because I'm gonna define the parameter tau, which is the complex time, and then if I take this quantity rho, when I was for a Lorentz invariant theory, this was minus tau, minus t plus x squared, becomes a positive quantity, which is just the radius of some sphere. So if I define this quantity and then I look for O4 symmetric solution, then the problem of the finding the bounds reduced to a one-dimensional problem, basically, where I have this equation that has some friction term and where the boundary conditions are given by at rho going to infinity, I'll be in the false vacuum, and then the derivative of phi with respect to rho at 0 is 0. So this boundary condition is just the fact that there is a, it's just the fact that there is a turning point when where the solution goes from the false vacuum to the true vacuum. The interpretation of this is that because at infinite radius I have the false vacuum, is that there will be quantum fluctuations that will be creating bubbles of the true vacuum. Okay. So, okay, I can then, just given these solutions, I can put them on a computer and solve them and then find the probability by replacing this into the Euclidean action, the solution into the Euclidean action. But there is a way of making progress by taking some assumptions. So, to have some analytical understanding of all of this. So if I assume that the difference between the two potentials, delta V, is much smaller than 1, then the question of motion for the fields where rho is, it will be just this simple equation where prime is derivative with respect to rho. So if I solve this equation looks like the equation of a soliton where I'm on the true vacuum when rho goes to 0, I'm in the false vacuum when rho goes to infinity. So if I define the tension, okay, so then I can imagine, I was talking about this bubble, but in the thin wall case, I'll make this more precise. I'll have like a bubble with some tension. So the tension of the bubble, sorry, is given by this term from here. And if I compute the bounds, if I make the computation and then I replace back into V, I'll find that the bounds in the case of the thin wall limit will be given by these two terms. When one is the tension of the brain, sorry, the surface tension of the brain, and the other one is the volume of the vacuum. So that means that for when the tension is not too small, then this bubble will not be allowed to exist, but for some configurations, then the bubble will start growing. So if I extremize, this depends on rho naught. So I can extremize the action and find the value of rho naught and replace it, and then I'll find the value for the bouncing action. So good.
Sorry, Sebastian, what is the condition for the bubble to nucleate? I missed that.
No, okay. So because when I made I made this approximation, and then I can just find some analytic approximation for the equation, but I haven't extremized the action. So there will be several configurations for the path integral. And the one that extremizes the action is the one where there is an equilibrium value for the radius of the bubble. That means that if the radius of the bubble is smaller than this, then the bubble will collapse.
Okay.
All right.
I see.
Okay. So good. So okay. Okay, so now I have this picture of the bubble in Euclidean space, and I would like to know what happens after the nucleation. So I have this state, I will assume just by Lorentz invariance that the nucleation happens at tau equal to t equal to 0. And then I'm gonna rotate back the O4 solution to O1,3. And then because the bounds solution was only dependent on rho, it will depend on -2 plus x bar squared, which is implication from Lorentzian invariance. From there, I can just see that the bubble, I mean, there will be a bubble of radius r, which is related to r naught, which grows at the speed of light, and that will imply that if I'm on, I will only see the bubble when it crosses my light cone. So, okay, good. So, okay, all this, I mean, all what you have to bear in mind here is that there is this bubble that I computed using a Euclidean rotation, and then in order to understand what happened after the nucleation, I can analytically continue back to the original metric. So, okay, now I'm gonna move to talk about vacuum decay with gravity. So vacuum decay with gravity is a bit more dramatic in the sense that the vacuum energy seeds the Einstein equations. And then depending on the value of the vacuum energy, I can have very different spacetimes. So if the vacuum energy is positive, then I'll have an expanding or contracting universe. If lambda is 0, then I'll have Minkowski, which is the case I was studying before. But if lambda is smaller than 0, then I'll have anti-de Sitter, which is a very different spacetime with different properties. That is, in this case, will be unstable. So, but I can still make progress by just using the same prescription that I did before for the quantum field theory case, namely finding bounces. And furthermore, I will assume first that the bouncing solution doesn't break any symmetry. So I'll still looking for the maximum symmetric solutions. So an interlude, because I'm gonna be more interested in the Sitter spacetimes, is that in the case that I have the cosmological constant positive, I have something called the Sitter. So the thing with the Sitter is that it has a space-like horizon. That means that there will be an infinite surface of future time. And then I can foliate it in several times, and the most famous one are here. So the close, the Sitter foliation, I mean, so this horizontal line is time, and this the horizontal line is raw position, and the vertical line is time. So if I move in this, I mean, so this will be constant time slices, and this will be constant radius slices. So for example, for inflation, I'll get a flat slicing, or this is the most commonly studied in inflation. I mean, commonly studied foliation in inflation, where if I take a constant time slice, then if I fix time, then for a constant row slice, it will move to infinity. The same thing with here. Okay. So now I'll start looking for O4 bounces with gravity. So in this case, the situation is a bit more complicated because I have to generalize the Minkowski metric to taking care of the different possibilities. So I write the metric like this in Euclidean signature. And then the questions of motion are, the first one is similar to the case of QFT with the difference, and this term is a bit modified. But also for the radius rho, there will be another equation which is very similar to the Friedman equation. Okay, I can solve this equation in the same thin wall limit, and after doing the same computation, I can show that the bounce is very similar, or is almost exactly the same that I computed for QFT, with the difference that it will be, the decay will be more or likely or less likely depending on if I have energy positive or negative. So for example, for the case of transitions between the Sitter spacetime, the bouncing is given by this, where in the thin wall limit, where T will be the tension of the brane, HA and HB will be the different cosmological constant for the two spacetimes, where H is related to V/3 and is 1 over lambda. So I'm using these three notations indistinguishably. And where A bar in this case will be the radius of the bubble. So of course there are more cases when, I mean, there are more cases than decay between the Sitter and the Sitter. I can have the Sitter to anti-de Sitter. But the problem there, or this, what happens if I decay from Minkowski or de Sitter to anti-de Sitter, is that the space will be unstable and it will be destroyed after some time. I can also have the opposite tunneling from the true vacua to the false vacua. That's what I have positive or negative sign here. But
sorry, Sebastián, sorry to interrupt. That statement that that anti-de Sitter is unstable, is it because you have a transition, or is it just that anti-de Sitter is unstable? What is the?
Because I have a transition.
Okay, okay. So you can have anti-de Sitter, but you cannot go into anti-de Sitter. Is it something like that, or?
Yeah, that's the statement.
I see, I see. And so what is the end result of that process? Is the bubble that simply goes back to the previous state, or what?
No, it's a big branch, so the bubble will blow away.
Okay, okay. And but what happened there? What's the?
No, what happened?
I'm just trying to imagine what happened.
Doesn't exist. So you have a big branch where you have a singularity. So the space-time becomes singular after some time.
Okay, and is this settled already? Because I remember, let's say 10 years ago, this was still something people were not sure about. I mean, what really happens when you move from de Sitter to anti-de Sitter, and the status was not really clear. So I was wondering, well, what has been the progress since that discussion?
No, I think it's set. I mean, so now because people are worried about this because the Higgs develops an anti-de Sitter vacua at higher energies when you include loops.
Okay.
Right. And then the solution for that is that the decay time from our vacuum to the anti-de Sitter vacuum from the Higgs is larger than the age of the universe. So we will never see it.
Okay.
I mean, there's so also, I mean, on top of that, because you can include supersymmetry, and you can say that, okay, anti-de Sitter is supersymmetric, but then there is a theorem by Weinberg that says that you cannot decay from a positive cosmological, a positive energy vacua to a negative energy vacua when you have supersymmetry. So in that case, that's forbidden by other reasons. Okay, but it is not then like, okay, this is non-perturbative in some sense, and therefore we don't really know how to, or let's say strongly coupled in some sense. Well, this is non-perturbative. So yeah, no, forget about non-perturbativity. Let's say it simply is a regime that we cannot really describe with okay, it might be that you cannot describe classically what happens after the nucleation, but the fact that it will develop classical instabilities. I mean, you cannot describe what will be the quantum effect of after the tunneling, but there is an effect that after the tunneling from de Sitter to anti-de Sitter, the space-time will be classical and stable. Right. Okay. Okay. So I was talking about the bouncing solutions in de Sitter. Okay, and I want to see what happens. I mean, let's now imagine that this decay that's described in this picture happened. So I have a transition from the false vacuum to a true vacuum. And then I want to ask, how will the universe be after the transition? So one of the things of the Coleman-DeLucia procedure is that there is a very nice picture of what happens later. So the main thing is that, okay, so in the Euclidean spacetime, I have these two bubbles glued together by a wall in the middle. So if I move, this will be the O4 metric. And then if I move chi, I will be in one side, in one of the hemisphere in the false vacua, and in the other hemisphere on the true vacua. Then, okay, I want to take the solution and analytically continue to go back to something that's Lorentzian. But I want to bear in mind that I have to still have in one hemisphere a false vacuum and the true hemisphere a true vacuum. So if I rotate this coordinate side and then I analytically continue it, then I find that the spacetime is described by the central patch on the zither, where for constant chi, I'll have constant chi slices are slices that move like this. So, for example, if the radius of the bubble was rho naught, then this will be the slice described by the radius, and in one side I will have the false vacua, and on the other side the true vacua. Okay, good. This space-time, as you can see, doesn't describe what happens on this part. So I cannot use it to describe inflation, for example. So the way to go is that I can analytically continue the solution, this pink solution, to the blue region by doing these two other analytic continuations. And if I do that, then I'll find that the space-time described in this blue region is given by this metric from here. Which you can recognize is a Freeman-Robertson-Walker metric, if we assume that rho in this case is the scale factor, and with the peculiarity that the slices here are open slices. So it's like when you write it down with SO2 symmetry and K is negative. So there is a more complete picture of this because the tunneling didn't happen between 2 points. So I mean, this is the current way of thinking about this. So I have a false vacua on the point A, or far from the point A here. Then the field will roll down towards a point 5A that will satisfy the boundary conditions, and then it will tunnel to another point 5B that will satisfy the boundary condition. And after that, this field will roll down up until it reaches the true vacua. So in this picture, the true vacua will be Minkowski, and then that's where I don't have a space-like surface, but I have an infinite point. So the main statement then from this transition between the zitters is that I have an open universe predicted. So open universe can also explain inflation, or can also be, are compatible with inflation, in the sense that if I tunnel from this point 5A to the point 5B, the chromosome, and I look for initial conditions which are given by this, then the initial conditions are given by just the turning points, is the point where the momentum goes to 0. So initially curvature, this might be at some point very high in the potential that is far from a slow roll. But what happens is that initially the universe is dominated by curvature, and after some time, it will freeze down until it reaches a plateau, and is a solution like inflation can happen. Moreover, there is we need this thing to happen because the thin wall limit is only consistent in the case that V prime over V is larger than 1, which is the total opposite from the slow roll conditions. Okay, this will wash out all the curvature, but for some certain situations, it can be that it will be possible to see some curvature, and I will talk about that more later. But just as a clarifying, we haven't observed any curvature in the universe, and then the limits are very strongly suggest that the universe is flat. Okay, so all this nice picture came with, so these papers have almost 40 years, or have 40 years. And there's been some criticism, in particular, because I made a very large use of analytic continuations. So one of the analytic continuations to get the bounce, that might be okay, but the fact that I got an open universe was after doing several tricks. So this is not very transparent, and there are some people that don't believe in it for a number of reasons that I'm gonna describe now. And then there are other problems based on this Euclidean picture, namely that if you perturb the solution, then you'll find that there is an infinite number of negative energy modes, which are not allowed when you look at the Minkowski case. But this will happen when you have transitions between the zeta. Also, there are some other more general cases where I can transition from a black hole to a de Sitter spacetime when instanton are singular, but nevertheless, I can compute using other methods the transition decay. So it will be then very nice to have a Lorentzian picture of vacuum decay. The problem is that this is not yet available. So I'm gonna now talk about some ideas that people have used and some ideas that we propose to understand this problem. So okay, this can be solved this is what the thin wall limit is very important because it's important also because I can fully solve the problem in the case I have a thin wall that from now on I will call a brane. So now this will be a problem of quantum gravity, and one of the main problems with that is that the Hamiltonian doesn't depend on time actually because of the general relativity is different from physically invariant, then the Hamiltonian vanishes. And that implies that the Schrodinger equation is replaced by this equation, which is called Wheeler-DeWitt equation. So before solving the problem or solving the quantum mechanics problem of finding the transition between the two spacetimes, I can look for a simpler problem, which is the dynamics of a brane that moves between two de Sitter spacetimes. So before I just was describing this using Euclidean methods, and now I will do the same thing but using Lorentzian methods. So the way I do this is just by, you can imagine this like a problem in classical mechanics. So I have a membrane separated into spacetimes, and then I want to make the two spacetimes be continuous at this point. So this is done by imposing boundary conditions that the difference over the induced curvature at each point is equal to some surface term, which is integrated over a small region here. So now I need to define a way to describe this metric. So because this cannot depend on time in principle, then I'll make use of this parameterization of the spacetime which is called the static patch that doesn't depend on time. So this metric this metric represents the causal patch of an observer at a hemisphere. That implies that if the wall is, this radius r will be related to the distance from the hemisphere of the false or true vacuum to the wall. I'll also need the internal metric of the wall, which is just given by this because I'm going to assume that SO3 has spherical invariance, rotational invariance. Okay, so if I analyze that problem, then I'll find an equation for the radius of the wall. So the radius of the wall is given by this simple equation that I can interpret as a potential. And what I find is that there can only be a wall starting R valued R0 that depends on a combination of the two vacua that can grow after time happens. So that implies that the wall will appear at R0, so it can start from 0, and then it will start growing. So just to be more quantitative, I can solve the same equation than here in global coordinates because that's where I can draw the Penrose diagram. And then I'll find that the trajectory of the wall in global coordinates is given by this. And if I plot it, I find that the wall metric is given by this red line. So this is very interesting because this is exactly the same trajectory that I was finding by going to the Euclidean case. So if I fix chi in that case, I will find that the equation for the wall was the same one. But now I'm not assuming anything about the bouncing or anything like that. So okay, now this only gives me half of the spacetime, and I want to compute what happened before the tunneling, what happened before I got R0. Sorry, what happened before the radius of the wall was R0, and if I can relate this to probabilities. So okay, so I'm gonna look at the Wheeler-DeWitt equation. I'm gonna look for solutions that look like exactly the same I was doing on my first slide, just using a Dirichlet approximation. In this case, there's no reason why I can drop one of the solutions. So I need to keep both. I'm going to define probabilities as the ratio between the wave function over this state, which is a composite state where I have an true and a false vacuum separated by a wall, and a background state where I have, so let's to say, the true vacuum, although it can be anything. So if I do this, then I will find that the probability of going from this state to this other state is given by the real part of these two terms. I mean, I in this case is IS. So it will be the difference between S minus S evaluated on N minus S evaluated on the background. And I can write this like this in terms of formula. More importantly, if I look at the Sitter spacetime, this should supposed to be the correct picture of how one will think of the Sitter on a Lorentzian picture, of the tunneling with the Sitter space on a Lorentzian picture. That is, so initially I have the Sitter spacetime, and then after the transition, I will have two de Sitter spacetime separated by a wall. Then if I compute the ratio between this state, the wave function for this state over the wave function of this state, I'll find that this is exactly the same coefficient that I found for the CDL computation. Although now the meaning is, at least for me, a bit clear. Okay, so okay, so one of the other things that is important, sorry, is that before I mean, this is all the thing that I can infer from this, from solving the Wheeler-DeWitt equation. I cannot say anything about what is the slicing of the spacetime. So in this case, the fact that I can either put open or closed slicing, and that will be, and what I will find will be given by observation. The problem with having a closed slicing in this case is that the universe will be inhomogeneous, because for the open slice, I can find a line of constant radius that takes me from T to infinity. Okay, this approach has been known from some time, but it hasn't been possible to generalize it to include the scalar field. So there is a lack of understanding on this, and some people doing progress on this area. What we can do is to look at some kind of simplified problem, which is going to something called mini-superspace. So mini-superspace is, in simple words, an approximation of the spacetime where I have that the metric is SO2 invariant. I have a closed universe, and then the space of metrics represented by this value n. It is very important when I want to solve something called quantum cosmology problem, because it's tracked out. So I can make conjectures using mini-superspace and then try to see if they are correct or not. So, okay, one of the main difficulties you can see here is that if I write the Hamiltonian, the metric from the Hamiltonian is not positive definite, because if I try it, I will have to treat A, the scalar field A, sorry, the scale factor A as a field, and it has the opposite sign of phi. So this will cause a lot of troubles. So if I, for example, if I assume that I have a potential, then the forbidden region, which is in black, make a lot of different things. It's just not only studying a multi-dimension, multi-field problem, but you have to take into account that the signature of the kinetic term is different. Okay. Nevertheless, if I write this as a WKV, if I write this as a WKV on the WKV approximation, I can find some solution for the equations of motion. So I can transform this problem for the Hamiltonian, and apply the Wheeler-DeWitt equation, and I can reduce this to this equation, where this function f is given by this term from here. I have some ambiguity because I want to treat, this is like when you do quantum mechanics, right? So I want to treat the momentum transforming into a derivative of S. It's something similar to what we do when we quantize a field. And I have to keep track of this sign CS. So if I do that, then I can find that the action S0 is just given by C to minus 1 over F, where S is some affine parameter. So then I can use this formula to study vacuum transitions. So for example, if I have a constant potential, let's assume that V0 is constant, I can still have some kind of tunneling. So I can do the same computation. The reason why I have tunneling is because A changes on time. And then if I write this, the derivative of A with respect to S, and this is just the Friedman equation, then I'll find that for A cube V0 smaller than 3A, then S2 minus 2S is equal to minus 1. This is some kind of under the barrier region. And if I compute the action for S0, I'll find that this will be equal to 12 pi squared divided by V. And then if I compute the wave function for this case, that means that I squared this will be plus or minus 2 pi squared divided by V. So this factor is similar or equal to the, depending on the sign, to the entropy of the sitter. So I'm computing the entropy of the sitter based only on some kind of a WKB approach. So depending on the sign, I have two different interpretations. One is the Hartle-Hawking approach, and for positive sign, and when I have negative, it's called tunneling approach, and it's called negative because it has a negative sign. It looks like a tunneling decay rate. An interpretation from all of this is I'm tunneling from nothing towards some space-time that is expanding. So, for example, if I solve for the scale factor, I can find that the scale factor after in the allowed region, for the classical region, is an expanding space-time, but for the forbidden region is this is the other way around, but okay. So for the forbidden region is a sphere, and for the allowed region is a expanding space-time. And I can picture this and this trumpet that start from a circle. This is why this is also called no boundary proposal, because the way that you can imagine the space-time as a solution from the Wheeler-DeWitt, basically what we're doing is we're finding a solution for the Wheeler-DeWitt equations that give me a de Sitter space-time that is expanding as our universe. And furthermore, then we're saying that there's some region, instead of having a singularity, then I'll have some region which is Euclidean, so I'll have some sphere. So this will have no boundary. Okay, I can add a scalar field to this picture and ask the same question that I did for the quantum mechanics case, and I'll find the same transition probability. This is some kind of cheating because I had what I was doing is basically a mini-superspace computation. So when you do CDL, when I rotate, when I go to the forbidden region, I have an enhanced symmetry, which is 04 in the forbidden region, and it looks like CDL, the same thing that I was showing you before. The problem now is that for a closed universe, I have different boundary conditions, and so this decay is not allowed. I can though have different decays. So if I look at this potential, if I look at the potential of, and the situation where I have a false and a true vacua, and I can also tunnel from one vacua to the other, but the difference here is that I have no wall in any case, but I have, the picture here is that I have a contracting universe that then suddenly transitions to an expanding universe. And if I want to put a wall, then I'll find that after minimization, the wall doesn't contribute at all to the bouncing decay, and I'll have this. So this positive or negative sign are just because the sign ambiguity that I was telling you before. There are more general solutions if I allow that the boundary conditions are different. And then, for example, I can go classically from one region to the other and then tunnel back. And this is all allowed as a solution from the Wheeler-DeWitt equation when you have a mini-superspace approach. Okay, so all these points that even though in the CDL picture the universe was closed, there might be other decay channels in the landscape that will give me a closed universe. So then I will have to take a closed universe seriously as something that will be a product of the landscape. So for example, I mean, I can do a simple exercise of studying a closed universe decaying from one vacua to the other. So I'll solve the Friedman equations. So the difference with the flat universe is that there is this term here which has a negative sign that depends on that comes with the curvature. So the main effect that this term will have is that there is a minimum radius. So the boundary conditions are this, and then I have that there will be a minimum scale factor given by 1/h. So if I assume that I have some kind of a slow roll solution in the sense that I can solve for the scale factor and it will be given by approximately this, I can show that there will be, to explain the size of the universe today, there's a number, a finite number of figures that I can have. So this is because I have a mean, which is 1/h. In the case of a flat or an open universe, this a mean can be 0, and then this term goes to infinity. Okay. So now I'm reaching the end. So I can go a little bit beyond, I mean, it's hard to go beyond mini-superspace, but I can add perturbations to it. So one of the way of adding perturbations and then getting time is that if I can write the wave function as two separate wave functions, where psi of A will be the mini-superspace solution, and chi of A and phi will contain the perturbations. So if I replace back into the action, then I'll find that the equation of motion for chi is given by this. So this term are fluctuations around the mini-superspace solution, so are very small. And it can interpret by using S0 after solving it as a time derivative. So if I do that, then I'll find that I have two different Schrodinger equations under the barrier and over the barrier. I can solve these equations if I assume a spherical if I expand my field in terms of spherical harmonics, I can find for a space-time which is in the zeta that the perturbations will be like this. So this is our known result from people familiar to inflation, and if I compute the 2-point function, it will be given by this guy of here. So a way of thinking about this and how we can relate this to our flat space-time intuition is that if I take L to be very large, so L for very small, when L is very small, it will fill out the curvature of the universe. And when L is very large, the effect of the curvature will be very suppressed. So that means that a large L, I can relate this to the more familiar Fourier coefficients. So for large L, this goes as 1/L cubed, which is the same behavior that I have for a scalar field on the zeta during inflation. Okay, so now there are some observable effects of all of this, but as I told you before, inflation in principle washes out all the curvature. One of the advantages of inflation is actually it does that, because it's very hard to have a universe without curvature. But by the expansion of the universe, inflation will eliminate most of the curvature. So the density, I can still compute the density perturbation in a model independent way, where in this case, Q is the Fourier number and K is the curvature of the universe. And then you can see that the power spectrum is different at small Fourier number, depending on the curvature. This might have an effect on the low LCMB modes, which is given by this. So again, for small L, I can have that the CLs from the CMB can be either enhanced or suppressed. So this effect was studied some 10 years ago because people thought that it could solve the Planck anomaly. Okay, so now I reach my conclusions. So I hope I could convince you that even though there is a nice interpretation of vacuum decay with gravity, there are a lot of things to think about. So one of the main advantages of Coleman de Lucha is that it gives us a very intuitive picture, but even though it's nice to have that, I will like that will be better justified. One of the I mean, one of the ways of making progress is maybe looking at mini-superspace, but from there, we see that there is the main product is that you have closed universe. Maybe because you start with them, but you have to take them seriously. And another reason why this is important is because there are a lot of unsolved problems related to the landscape that needs or for a better understanding of vacuum decay. So this will be very important if you want to compute corrections to the decay rate. And this has been recently used to explain, I mean, the multiverse to explain the mass of the Higgs. Okay, so that's all.
Thank you, Sebastián, for your nice talk. We have some time, so if anyone has a question, please go ahead.
I have a question about one of the last statements, I think in the previous slide, if you go back. Yeah. So you say that you can either suppress or enhance the power spectrum, but I look at your expression there, the equation below, and I read from that equation that you only suppress it, or does it depend on K, which can have either sign?
Yeah, K can have either sign. So this is in general for positive or negative curvature.
Okay, I see. And does that result fits better than the the flat spectrum at low L's?
Well, for some time, a closed universe was a better fit for the low L modes.
That's not longer true?
Well, I'm not sure now. I guess I guess because it depends on which observations do you add to it. So if you do it only with the CMB, with Planck data, yes. If you add baryoacoustic oscillations, then no. Then you have that the flat universe is favored. And there are still people claiming that the universe might be closed. But okay, the problem is that there are no very well-known mechanism why the universe is closed. So, because the main way of, from tunneling, you mostly get an open universe.
Mm-hmm. I see.
Any question? No? Okay. We are...
Actually, I have a quick question. I remember seeing... No, I remember that you said that this had some implication to the string landscape. I'm not very expert on string theory, but naively, it does depend on the string theory that you're doing, or it's in general for all strings?
Yeah, it will depend on the string theory you are doing, but there is there are different ways of populating the landscape, and the main way is by putting branes and then having different universe to collapse or not. So the way this bubble will collapse will depend on the geometry of the bubbles. So if you have open bubbles or closed geometry, bubbles with closed geometry, then you'll have different outputs. But this is more like a phenomenological modeling of how the decay will happen, because it hasn't been well understood yet.
Okay, thank you.
So what could be a feasible picture of going from one de Sitter to another de Sitter space-time in the early universe? For example, will it be feasible to have this during, let's say, not inflation, but let's say during a radiation-dominated era, for example, just to where okay, the geometries are very suppressed, but still the effects of the transition might be relevant, for example, for, I don't know, enhancing, for example, the amount of radiation, let's say.
Yeah, it might be. The problem is that after the tunneling, the universe is I mean, the scalar field is accelerating a lot, so you don't have a constant curvature mode there.
Mm-hmm.
So I say that you could have, I mean, you could have seen that in the CMB. I mean, having an open on a closed universe or such a thing happening in radiation will change a lot how the CMB peaks look like.
Right, right. Because this, okay, so in a sense, you pump energy into the universe. This isn't some, I don't know if this is in the walls of the bubble, I guess, right?
No, okay, but okay, so you're right. So for example, there is also a proposed solution to the H0 discrepancy where you have tunneling during radiation from another scalar field. So that could happen.
Yeah. Okay.
So it's a way of pumping energy, as you were saying.
That's what I have in my mind. If this is something that people has looked into, for example.
Yeah, there is some work by Martin Sloth, I think.
Okay.
No, because it's true. So, I mean, it won't be the inflaton because it won't be responsible of the curvature perturbations because that's already constrained, but it can happen for other fields.
I see. Okay, and this has the potential to solve the H0?
Well, they claim so.
Okay. And this is because it just pump energy into the radiation bath. Okay.
Yes.
So you refer to these early dark energy models, right? Or not?
Yes. Yeah, I'm thinking about that.
Yeah, okay.
And will you with them? Do they use similar tools to what you're doing here, or?
I mean, they're using CDL mostly. So they're not worried about the curve, I mean, the geometry of the universe after their transition. But yes, so probably radiation domination, you don't even need to include the effect of gravity. The effect of gravity will be very suppressed.
Probably.
Right. So all these CDL, I mean, all these effects are more dramatic when you are very early in the universe.
Right.
And then also the picture when you have Minkowski spacetime is well established, so it works fine, and then you can do it in several ways. So and that has been proven. Also, the thing is, for example, the fact that the bounce is so symmetric has only been proven when you have Minkowski spacetime. So for when you include gravity, that's not the case. Precisely because you have this problem with the negative sign of the scale factor.
Okay.
I think we have some time for a very short question. We literally have less than 3 minutes. Okay, if there is no more questions, so thank you, Sebastián, again for your nice talk, and thank you for everyone for coming today. I hope to see you again in the next time.
Bye.
Bye.